Yeah, okay, so let's get started. Thank you for joining. So today is our third session of TF Club, and today we are going to continue talking about the estimator API. Last week we said the estimator API is the highest level of abstraction in TensorFlow, and it has many advantages that we don't get when we build custom models. And the advantages we said, we can quickly try different kinds of pre-made models. We don't need to write many code. Like if we are to build a custom model, and if you want to try a different one, we have to modify many lines of code. But with the estimator API, we can just make very small lines of code, change of small number of codes, and try different models. And also it helps for checkpointing, like it saves the model results as it trains every some intervals, and we can use this checkpointing. It helps us to resume on failure or continue training, and also while it is being trained, we can evaluate how the model is performing. And the other advantage is it helps us to train with out of memory large data sets by loading progressively. And as I said, for evaluation during training, because we are saving the model weights intermittently, so we can use the most recent weights to see how the model is performing. And it helps us for distributed training. And another advantage is hyperparameter tuning on Cloud ML if we are using Google. And today let's start with how a machine learning model learns. Like, let's say we have simple data, 2 columns, y and x, and let's say the relationship follows this equation: y is equals to ax plus b. Where is my cursor? That's weird, I don't see it. Anyway, so let's say we have 2 columns, y is equals to ax plus b. So in this case, y is our response and x is our feature or our predictor, and a and b are, a is a coefficient and b we have the constant value. We are just taking the simplest case, but we can have many features like a1, x1, a2, x2, and so on. So the first thing the model does is it has to come up with such kind of representation: y hat is equals to a hat x plus b hat. So those that are, these are approximations. That is why we are calling them hats. With initially what it does is it randomly picks values of a hat and b hat. So the first, machine learning is an iterative process. So first it picks random values for a hat and b hat. So in that case, we are going to get a corresponding value for y hat. So once we get the value of y hat, we can calculate the error. There are different error measures that we can use. If the data is, I'm assuming here, continuous y values, and one of the error measures is mean squared error, which is given by this one, like the difference of the actual value and the predicted value squared, average of that. So as you can see here, we are squaring it, but you can also take mean absolute error. But this one is more commonly used. One reason being it is easy to differentiate, and the other point we cannot share is this is very sensitive to outliers because we are squaring it. So what we are doing in the machine learning in the different iterations is we are trying to minimize this error, this mean squared error, or we can have different other errors. This error we call it loss function or cost function. So, and the loss function, it is like similar to a hilly landscape. So we have here such kind of hilly landscape, and the first time we pick the values, randomly pick the values of a hat and b hat, the error is very high. So we see it is at the top here, like we have large error. And in machine learning, what we are doing is by iterating using different optimization techniques. There are different optimization techniques that are built in TensorFlow. By through iterations, we are trying to come up with, to get the lowest points in this landscape, and those lowest points correspond to the optimal values of y hat and b hat, and that is what machine learning does basically. And a couple of points here, when we do like this, like for the optimization technique, when we have features, like the features are the x's, when the features are in different units, we have to scale it, because scaling the features helps us to quickly convert to the lowest point. And there are a couple of different feature scaling approaches. One is normalization. Like here, what we are doing is we are subtracting from each data point, we are subtracting the corresponding mean for that feature and dividing it by standard deviation. We call it normalization or standardization. There is also min-max normalization. So for every data point, we subtract the minimum of that feature and divide it by the difference of the maximum minus minimum. And if you go to TF-Keras, there are different optimization techniques that help us to come from to get the lowest points of that hilly landscape. And usually Adam and Adagrad are the default for many of the built-in machine learning models. They are flavors of gradient descent, of improvements of gradient descent that handle different issues. Like some of them handle like to avoid getting stuck in a minimum, in a local minima, and so on.
What's a local minima?
So local minima is, if you go here, for example, in this hilly landscape, the actual minima could be, yeah, okay,
there in the middle.
yeah, it could be here, but there are other local minimas, and if it gets stuck somewhere, it may not come out. If it goes here, probably it may not come out, or it may start here and fall to this point, and then it may not go out. But there are improvements to gradient descent, like momentum and so on, that handle such kind of problems. The other important issue related to, because we talked about the feature scaling in TensorFlow. So last time you asked me about using beam, right? With transform. So in TensorFlow, since we are loading batches of data, we can, if we have to standardize the data, we don't have access to the global minima and global maxima of the data. So in that case, what we have to do is we have to get the minimum and the maximum of the features outside of TensorFlow. And similar thing, if we are also to find, when using feature column, if we are creating categorical column with vocabulary list, the list of the vocabularies also we may not know them. So in that case, we have to process our data outside of TensorFlow and get these values. And generally, for feature engineering, we can use this Google product. BigQuery is one. We can also use Spark or any tool that helps us for batch processing. Apache Beam, and TensorFlow. So there are things that TensorFlow doesn't do. If TensorFlow doesn't do it, then we have to use either BigQuery or Apache Beam.
And of course, this is only the tooling in Google.
Yes, I said Google products.
Right.
Yeah, we can. So for the BigQuery, we can use Spark or any tool that helps us for batch processing.
There's also data prep.
Yes, data prep actually uses.
Right.
Yeah,
but as a user interface, you don't really see the batch.
Right.
The beam part.
Yes.
It's worth mentioning what Apache Beam buys you in terms of integration with TensorFlow, which I was pointing out last time, that you can, as Fish was saying, you can do this pre-processing with Apache Spark. The only difficulty is when it comes to productionalization. How do you make sure that at a web endpoint or a on-device?
Yeah, I mean, if you are making batch projections, still it is not a problem. But if it is like if it is streaming, it doesn't work.
Sure, streaming is a different use case. What I'm talking about is batch. Because I did this a lot at my last job.
Okay.
We would write production code to process big data with Spark.
Okay.
And then our deployment platform was a computer with very little very few things. So when we wanted to deploy it, we wanted to deploy it as a C++ program. So every time you change the processing, you have to rewrite the Spark code as C++. Beam actually, it supports with TF transform packaging those pre-processing procedures that you do with big data, with streaming, batch. into the actual computation graph
I see.
of the TensorFlow graph. So you can actually deploy that with TF
Yeah,
Lite or whatever other.
I want to add
TensorFlow does.
something to that.
Yeah.
When you're coming to TensorFlow, right, the only thing that you write is you write an input function which will read a bunch of records. So it doesn't matter if that bunch of records come from Spark or Beam or BigQuery. It can be anything. I just need some data sitting somewhere that I can read.
Yeah.
So it doesn't matter where it comes from, right?
Yeah.
Yeah, but what I'm talking about is ease of deployment.
Yeah. And in this slide, it shows where each technology is more appropriate. Like for example, if it is batch processing where we want to remove data that we don't want to use, or if we want to compute aggregators, we can use BigQuery or Beam or Spark. But if we are computing time window statistics such as number of products sold in the previous hour, in that case we have to use Beam. And in TensorFlow, if we have the aggregators, then we can pass them the aggregators to TensorFlow and write a function and add another feature, another engineered feature to our function.
Just for people in this room, be cognizant of, that's fine. Just be cognizant of this is where the microphone is.
Okay, thanks. Okay. And now let's go to the representation of deep neural networks. So last time we said neural network has been there since the 1960s, but recently, because of computational efficiencies and better optimizations and better algorithms, people have enabled to use many layers of neural networks in their model, and that is why it is called deep. Otherwise, the concept of neural network has been there. And what I'm seeing here is, like in neural network, the input layer, the first layer, the input layer is features. Like for example, in this case, I have 1, 2, 3, 4, 5, 6, 7, 8 features, and each feature is multiplied by some weight. And when I multiply each feature by some weight, I am getting in the first hidden layer we have nodes. This number of nodes and the number of hidden layers is something that we can fine tune in our model. So we get nodes, and in those nodes, once we get the product of the input layers with the weight, then we have to transform the product using some kind of activation function. This activation function helps us to capture non-trivial, non-linear relationships between the data and the output, basically. So as you can see, we have in this case 3 hidden layers, and this is classification. In the output layer, we have 4 classes, right? And for the activation function, there are different activation functions, and it is an area of active research. Every now and then there are new activation functions. Before a couple of years, sigmoid and softmax were very common. Then came ReLU, then came flavors of ReLU. And as you can see, for example, if we see ReLU or the rectified linear unit, if the product of the previous layer and the weight is greater than 0, it takes that value, but if it is less than 0, is 0 or less than 0, it makes it 0. And we have also tanh, and softmax is another activation function. Softmax, we use it at the last layer or the output layer when we have more than 2 classes, basically. And sigmoid is also another common transformation function. It gives us like a probability between 0 and 1, and you can see the equations for each one of them. And all these activation functions and other activation functions are built in the TF-Keras API. So under activation, you see we have ReLU, sigmoid, softmax, and other tanh and flavors of ReLU. And the other point we should quickly mention here is, like, so when we build machine learning models, we divide our data into 3 sets. We have the training set on which we train our model, the evaluation set on which we evaluate our model performance, fine tune it, compare different models, and choose the best model the best model and also the best model hyperparameters based on the evaluation data. Whereas finally we check on the test data, and that will be the performance metrics that we report that our model's performance. So here what this slide shows is we have the loss. What we show, like in the previous slide, we showed this loss of this one, mean squared error, or we can have other kinds of losses based on the kind of model we are building and the loss type we chose. So we have here, it shows how the loss changes. So machine learning is iterative process, and in each iteration, if the machine learning is doing a good job, the loss should be decreasing. But we want it to be decreasing not only on the training data, but also on the validation data and the test data. So here what we see is, like, you see, after some time, the red line, it has started increasing. The loss has started increasing. So this is a sign that the model is overfitting. Rather than generalizing, at this point, it has started memorizing the data. And there are different techniques to solve this problem. Early stopping was common before some time, but these days there are many people that oppose it, because even if it increases initially here, if you train it, if you give it more time, after some time it may decrease and start learning more. So rather than early stopping, people recommend different regularization techniques, and especially in deep learning, the dropout is the most common type of regularization technique. So as we saw last time in dropout, what we are doing is we are randomly dropping some of the weights, some of the connections between the previous layer and the nodes in the current layer, and this helps us so that the model doesn't memorize noise. And okay, so let's see how we can build a deep neural network regressor, what the requirements are. Like last time, we saw how to create the feature columns, and we said using some list compression is very convenient, especially when we have when we have many columns. And for those of us who were not here last time, let me quickly show the list compression, how it works. So what we did was, like, list compression, if you have in here, if you can see this, I have a list of 11 numbers from 0 to 10, and if I want to square the even numbers, to get square of the even numbers, I can use this for loop, or using list compression, simply I can say if each element of these numbers, if I call it a number, then I can say number square for number in numbers if modulo of number by 2 is 0. So in that case, it will give me square of each number. So generally, list compression is very, very handy, like when we use Spark or TensorFlow. In such cases, we say it. And this one was an example that we used it in our project, and it has about 400 columns. So rather than creating TF feature column, numeric column for each one of them, we can identify first the numeric columns. We identified them using the prefix C underscore here. All the numeric columns have this underscore, and also there are actually other ones here. So we created the list of numeric columns. So for the list of numeric columns, we created numeric feature columns just using this single line, rather than writing 400, 300 lines for each one of them separately. So list compression is very nice, we said. So to come back to the slide, so once we create feature columns, the next thing we have to provide is the hidden units. So hidden units is 10, 5 minutes. This is the number of layers that we are specifying here. Yeah, so based on our intuition, the complexity of the model, of what we are trying to model, and the data size, and the other thing is we try different architectures, different number of hidden units, and see which one works better.
To me, this is where the black magic happens.
Yeah.
Yes.
Right? Like, how do you decide, okay, what's going to be my activation function? How many nodes do I have? How many layers do I have?
Yeah.
What's the atoms part? Like how do you pick one of those?
Optimization.
Yeah, optimization.
So what you do is for the kind of problem you are working, probably people have tested it and they have written a paper. So you start with that. Otherwise, you try the different ones and see which one works for you. Because it depends even on the data that you are working. It varies from data to data.
So you really only need 2 layers theoretically. There's a paper that was released that said for most kind of data sets,
hidden layers or
2 hidden layers, and it's sufficient to represent any function.
So that's a good benchmark starting point.
And I think.
But then, like, how do you know whether to use ReLU or to use something more complicated, or right?
Yeah, I mean, like there are some guidelines. For example, if it is classification, and if it is output, since you need probability, you have to use softmax if it is multi-class, or sigmoid if it is binary, and if it is regression, you should not use.
Well, but that's the readout layer.
That's the output.
Yes, the output.
Right.
Yeah, the output, the last one. But for the rest, you try them, and also there are some theories on which one works on average better than the others.
For example, for certain recurrent neural nets, leaky ReLU is very helpful.
Yes. Yeah.
Well, anyhow.
Yeah. So I mean, it doesn't even sound science to me at times.
Yeah, it's like
Because you are just trying different things randomly. Yeah. But it works. It does the magic, so you have to use it.
And I think the difference is also not that much, right? Maybe like 3 or 4%. That's it between different models. You hit a benchmark, and the core thing is in TensorFlow is in the steps. It learns it so well. So if you use a better architecture, instead of learning in 1500 steps, it would learn in 900 or 800. You're basically shrinking your computation, but it's going to learn eventually.
That's the thing with ReLU. People were using sigmoid for a while as an activation function, and they realized that, like, even though ReLU didn't have this statistical basis that the sigmoid function had, it was enough to get the job done, and it was actually computationally cheaper than sigmoid.
So yeah.
Is there I mean, we've effectively reduced. This is the crux right here, right? This one line of code is like the crux of TensorFlow and deep neural network.
Right.
And there's like I said, there's not just one piece of magic and art here. The hidden units, the activation function, the dropout, the optimizer, and this is specifically after you've selected a DNN as opposed to an RNN or a CNN or whatever, right?
Yes.
So, are there? It feels like unless you know the underlying math, unless you've read all the academic papers on it, the person who is just going to, okay, we've made it this simple, anyone can just add a line, we can train it, and we can get something. Is there a cheat sheet, a flow chart of, all right, here's my work, I'm trying to do this, you should choose this type of network.
Generally, yes.
Network,
remember that white paper that Google's working on, which they use internally? I sent you that white paper.
YouTube recommendation?
Yeah, for hyperparameter tuning, which one to use, what would be the optimal number of hidden units. They already have an interface for it, and they're trying to make it available for everyone.
Okay.
But generally also it is known like which kind of, to a general person who reads about machine learning, they know which kind of model to use when.
But that shared collective understanding, there's only so many features. Treating this as a machine learning question itself, right? There's only so many features. There's the hidden units, there's the activation function, there's the dropout, and the optimizer. So, and the type of network.
Yeah.
Right?
Yes.
So
actually, this is the easiest part of the neural network.
Type is pretty cut and dry.
Okay.
Like you have a convolutional neural network for images. You have recurrent for time. There are other things, but like you have a GAN that has a very specific use case. Deep neural network is for more traditional supervised problems that don't fit into. But the interesting thing here is tools like AutoML that help you do this hyperparameter tuning for you. And actually, I don't know how AutoML is translated? Or
Do you mean Cloud ML, I guess?
Yeah, yeah.
Well, AutoML in general.
Yeah, I think it.
So AutoML is like you have the,
Transfer learning. Right?
yeah, very few, it does only very few tasks.
Oh.
So it doesn't do the hyperparameter tuning for you.
Or is so
But in Cloud ML, you pass ranges of
Yeah,
hyperparameters,
yeah.
different
Robot.
architectures, yeah.
I'm not sure about their secret sauce, but I know there was a paper a while ago, which is exactly what you were saying, Oscar. It's like this is a machine learning algorithm. So what they did is they described a neural network as a recurrent neural network where each layer is a sequence, an element in the sequence, and so then you can use this framing and you can do machine learning to get the machine learning algorithm,
Right?
Just kind of meta.
Yeah, I mean, there are, every now and then I read some magic that machine learning is doing, like it is by itself, it is learning how to write software program. It is learning also how to pick the best machine learning. There are such stuff. But generally, to the general public, people have to understand the models, but they are not that much complicated, I guess, if someone starts reading about them. Okay, so this is how we build a DNA regressor. We create the feature columns and specify hidden units. These are the only requirements, by the way. Most of the time there are default values, and the default values work fine. Like, for example, in this case, activation, the dropout, and optimizer. And if you are interested, we can try the other ones also. But if you go to the TensorFlow documentation, TF, so if you go TF estimator, where is it? Yeah, under TF estimator, for each one of them there are default values. So if you see DNA classifier, was it DNA regressor? DNA regressor, yeah. If you click DNA regressor, there is an alternative. Okay, and if you click this init, it shows you all the parameters, the arguments here, and you can see which ones have what default value. And then if you don't need those default values, you can modify them. So okay, so we have talked about hidden units, activation function, dropout, and optimizer. And generally, as we said last time, to build a machine learning model in TensorFlow, we have to define the feature columns first, then define input functions. The input functions, they pass the data for the training, for the validation, and for the testing. Then we instantiate a model that we need, and then call, train, evaluate, and predict. So the TF feature column is a bridge between raw data and the model representation, as shown here. So we have to have an input function. This input function, this one is, it passes the data, like the training data, validation data, or test data. So, and how do we pass it? How should it be represented? It should be like represented as a dictionary of the features and label. So we have, in this case, sepal language widths and petal language widths, and each one of them, there is a list of values. So a dictionary where the key is like the features and the values are a list of the batch size. The other thing we should talk about here is the batch size. So we said machine learning modeling is iterative process, and so to improve the weights, do we use the whole of the data, or do we use some size of the data? And it is found that using some like for example between 64 and 512, people use the powers of 2 because it is better in terms of performance, rather than using the whole data. Because if you are in each iteration, if you are training on the whole data, it will be very slow, it will take time. And if you are training on a single data also, you are not taking, it will be very noisy, and also you are not taking advantage of vectorization. So show the first, this one is stochastic, we call it stochastic gradient descent. So in each iteration you are taking a single data point. So this single data point, it will be noisy, but finally we'll get to the loss. You will optimize the loss and get the best parameters, but it will take time and it will be noisy, and they are not taking advantage of vectorization. But if we use mini batch gradient descent, like some size, not the whole data and not a single data point, like 64, 128, 256, and 512, and so on, it converges relatively quicker, and it has, it converges quicker. That's the advantage. So in deep learning, the other points, the other parameter arguments that we have to specify is the batch size also. The batch size is also required when we are training. So in here, what we see here is like the batch size. In the input function, we have the features and the level. So this list, for example, that you see here, this is the levels, and the size of this list will be the batch size, or the size of each list in these features will be the batch size. So the TF feature column is a bridge between the raw data and the model. So once we are passing the input data here, we have the TF feature column. We have defined what they are, whether they are numeric or categorical, or we have to specify the kind of data that it should expect. Then when we instantiate the model, we are passing it here. The feature columns, you have to find them under these feature columns, and they should be the same as the input data. So yeah, now let's quickly see like an example, the example solution. So in the training, first we used BigQuery to get the training and test data. But the train and test data, it is available online on the GitHub page I shared the last time, if you are interested to try it. But I just want to go over how we approach it, how we train a model. One, assuming that we have a data, and so there are two main cases when we build a data: when the data can fit in memory, and when we are training on large data sets. In this example, when we are seeing an example when the data fits in memory, so we can read it using pandas, for example, or it can be NumPy array for that matter. But like we have the training and validation test data, reading them using pandas, and getting the columns. So dftrain list gives the columns, or we can use a columns function with columns method. And here the feature columns are these columns except the first one. So we want to predict here the fair amount, and fair amount is the first column basically. We want to predict fair amount as a function of all of these other features. So we have to identify which one is the level and which ones are the features. And in Python, if you use like for example one colon, it means give me all the elements from this list, from the second to starting the second basically, because Python is zero indexed. So that means this CSV column names of 0 will be the first one. This is a fair amount. So we have identified the feature names, the feature columns, and the level name basically. And here we are using list compression to create feature columns. Since all of them, in our case, all of them are numeric, by the way. If they are not numeric, we have to use appropriate appropriate methods from the feature column API. And as you see, we create using list compression. We use a TF feature column dot numeric column, where the key is each element in the feature columns. And as you can see, it creates this. So we can pass this to our model when we instantiate a model. Actually, do you see a problem here? I mean, even if all of them are numeric, some of them, their numeric values doesn't mean anything. For example, day of week, we can represent it from 0 to 7, like, or hour of day, we may represent it from 0 to 23. But 0 doesn't mean
The magnitude.
Yeah, the magnitude doesn't mean anything, so we have to correct it. But when we have all the columns, when they are numeric, we can just use the numeric column key. And in this case, actually, the correct one to use is categorical column with identity something. There is categorical column with identity. So if you go to feature columns here, tf dot feature column, yeah. If you go here, we use this one, categorical column with identity. When we have numeric values and the numbers like are not, the magnitude doesn't mean anything, we use this one to change it to categorical data. And so I was here, yeah. Okay, so we have created the feature columns, then we define the input function. So the data, we pass it as functions, and we write 3 functions, input functions: train input function, evaluation input function, and prediction input function. And what should be the input function like? In the input function, we need the batch size. The batch size is what we discussed, and it should be powers of 2, basically we said. So the batch size in this case is 128. df is a data frame, pandas data frame, or it can be a numpy array. And the dataset API, it has a function from tensor slices. When we have data in memory, we use this one to create the tensors. So dataset equals to tf data.dataset from tensor slices, and the tensors should be represented as dictionary. The features should be dictionary and label. So this is a tuple of a dictionary of the features and the corresponding label. And so the dictionary of the features, in each feature there will be a list, and the list size will be the size of the batch. Yeah, the batch size basically. So once we create this, now we are creating a single batch, where if we just stop here, it means we will train on the whole data, but we need some batch size, and that is what we are doing here. To that data, it has this method. We have batch size here, so we specify the batch size here. The other point that we have to discuss is about shuffling. So our data, we have to shuffle it in 2 places. One is like in batch, we have to.
Could you expand the shuffling concept?
Yes. Okay. So shuffling is like, for example, if your data is ordered, if your level initially is 1 1 1 1 1, then at the end it is zeros, and if you just take the first 80% for your training, and the last 20% for your.
So it's a matter of getting an even distribution between.
Yeah, mixing it. Yeah. Yes. Yes. So we do it 2 times though. One is on the whole data, and in TensorFlow, especially when it is reading progressively, we want from those that has read in, the 1,000 records it reads, we want to shuffle it again. Why?
So that the many batches are different.
So sometimes you can find a local minima and you don't want it to fool you, right?
So it's avoiding getting stuck,
Yes.
in a valley up in the hill.
Yes.
It's also basically combined with dropout. You're seeing the same data set several different ways.
Yes.
Several different times.
Right.
So like there are these things called epochs.
Yeah.
Which you train. So that's one epoch is basically a full pass over the data set. But if we didn't do shuffling, then every epoch
would be the same
thing.
Right.
Which we don't want.
Yeah. So, and also to specify the number of steps, we make this repeat count is equals to none. That means this is indefinite. Until I specify the number of steps, just let it run indefinitely. So this is our input function. And for the evaluation input function, it is the same. The only thing is we don't need to specify the shuffling, because we just need prediction, so we don't need shuffling during evaluation. And during prediction, we don't have labeled data, because we have only features. So this is the input function during prediction. Once we do this, we have also defined our feature columns. Then we instantiate a model. So, by the way, TensorFlow, it is not only for deep learning; it also supports the other kind of traditional models. It can be linear model or tree-based models, gradient boosting, for example. So here we are starting with a linear regressor from the estimator API. and we have passed the feature columns, and we have to specify the model directory also. So specifying the model directory means like it will save the model output to that directory. Since it will save it intermittently, we have to specify model directory, and we also can specify other configuration settings. In this case, we are passing the random seed, like for reproducibility. And if you wanted to change it to a DNN, we just need to make only minor changes. So we have a DNN here. Okay. So once we instantiate our model here, the linear model, we have instantiated it, then we call train. And other thing here is the level of verbosity. We can control it using TF logging. It can be info if you want, like log level, or it can be warning, or it can be fatal if you want error. Yeah. And here, so we have model. The model has a train method. Train the input function. For the input function, we pass the training input function we created here. This training input function. And how do we pass it? Using a lambda function. If anyone is not familiar with lambda functions are like anonymous functions in Python. They'll pass single expression functions. Like for example, if I want to add two numbers, the traditional way, let's call it def add two numbers ab, return a plus b. So add two numbers 4 and 5, it will give me 9. But the lambda function is like this: add two numbers, the name, then lambda, this argument is, and what I want it to be. So it should be a single line. And here also the training input function, we pass it using lambda function. So the input function lambda train input function, and the argument df is the df train, because we have df train here created here in the beginning. We have read in df train, as you can see in the beginning. And so once we do that, and the other thing important here is the number of steps. So this number of steps, it will control this stage. Here we have said run it indefinitely, and if we don't include this, it will not repeat. So to make it repeat, we make it count is none, and then it will take the number of steps from here. And we can evaluate our model's performance. The model has an evaluate method, so we use evaluate here. We are creating a function print root mean square error for that model when I pass data frame. So this data frame is like the validation data frame. So model has evaluate method, so evaluate, and the input function should be the evaluation data. So we are passing the evaluation data, and from here it gives mean square error. And since we need root mean square error, we are calling it root mean square error. We are making the power of 0.5 basically. So this gives us RMSE, right? And to make prediction is the same thing. The model, it has predict method, so predict, and the input function is the same lambda function, and we use a predict input function and pass the test data. And this gives us a Python iterator, so generator, I mean, so we can iterate over it by using next or using other methods. And we can quickly change the estimator, like if you want a different kind of estimator, we use the linear regressor. And now if you want to use DNN, the only requirement here is hidden units. We have already created the feature columns, and hidden units we specify, like we are using here 10, and the number of steps was the same as before. We just train, and it has a default value.
Yeah, it goes by
Yeah.
from the run con.
Actually, in this case, I mean, even from the beginning, this approach, it has an issue. It is considering day of week, hour of day, and so on as numeric values. So this is just to show the steps that how you build a model, but the results, they are not worth watching. They are not worth like checking even. They are worse than the simply.
The best one. I think
Yeah.
you got 3.
Yeah, see, they are worse than the rules-based benchmark. This is some average. 7.76, whereas the DNN is 9.26 and linear model is 9.43. You don't expect any result from such kind of model. But you see the approach. This is to show the approach.
Yep.
Creating the feature columns, instantiating and writing the input function is instantiating a function, then training it by passing number of steps. And